Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to continue with the lecture number 18, and the title of this lecture is Program Components. What are the program components? Input and output instructions and the conditional jump instructions. So there are three main concepts that we will cover during this lecture. We will discuss about the program components like the .386 model and other directives that we were using in assembly language, and also the input and output instructions, and the last one is the conditional jump instruction. Now before that we will discuss that what we did in our previous lecture, lecture number 17. We discussed about the AND instruction, OR instruction, exclusive OR and NOT instruction. Inside the AND instruction we have two parameters, source and destination, and the bitwise operation will be performed if we execute this AND instruction between source and destination, and the result is again stored inside the the destination register. The next instruction was OR instruction, and this instruction uses two parameters similar to the AND instruction, and it performs the bitwise OR operation. And we discuss how this OR operation is being performed. For example, we have bit pattern 0, 1, 0, 1 and so on, and the next one is 1, 0, 1, 0 and so on. So if we perform OR operation, it will be 1, 1, 1 and 1. And if we perform AND operation for this same bit pattern, so this is the result of OR operation, and if we perform AND operation, then this will become 1 and 0, this will be 0, 0, 0 and so on. So we discuss all these instructions. Then there was exclusive OR. Exclusive OR instruction when these two bit patterns are two bits are pair is not similar, like 1 0 or 0 1. In case of 1 1 or 0 0, the result will be 0. In case of dissimilar these two bits, it will be 1 1 for the exclusive OR. Similarly, NOT instruction will invert all these bits inside the destination register, and again the result will be stored inside the destination register. After that, we saw some applications about these AND, OR and all these exclusive OR instructions and so on. Then we also used two other comparison instructions. Those include the test instruction and the compare instruction. And these two instructions are non-destructive, means in our previous instructions like AND or NOT, destination register's contents will be updated. However, if we execute test instruction, it will not however, if we execute test instruction, it will not modify any register's contents, but what will do, it will perform AND operation in between source and destination register. It will not make any changes inside these two registers whatsoever the result is, and between these two registers it performs AND operation, and if they are equal, these two operands are equal, then 0 flag will be set and so on. The next instruction was the compare instruction. Inside this compare instruction there were different comparison, like if we compare source and destination register, even though this instruction is similar to the test instruction, in this instruction it will not modify any contents of either source, either destination register, but it will perform subtraction between these two, source and destination. If they are equal, then 0 flag will be high. In case if they are like destination is less than the source one, then carry flag will be high. 0 and carry flag will be unset or 0 in case if destination is greater than the. So this is the overview of the previous lecture. Now we will start with this lecture. This is the outline that we will discuss, the topics that we will discuss during this lecture number 18. Now these outline includes program components. What are the program components? Then we will discuss about the IO instructions, then the jump or conditional jump instruction. Now this conditional jump instruction, there are different categories based on the flags, based on the equality, based on the signed comparison and unsigned comparison, and then in the end we will see some applications of these jump instruction and so on. Now First of all, the program components, we have used this .386. In assembly language, this directive tells the assembler, or this directs the assembler that it use 386 instruction set. You can use 486 privilege mode, 586 means Pentium, and you can use 686 means Pentium Pro, and so on, and their privilege modes. In the future lectures, we will discuss about their privilege modes and so on. However, we will discuss what are the other options that you can use during the at this place where we are using 386 directive. So right now, all these currently processors, they are the predecessors of the this 386 is the predecessor for the 386. So there are hardly any processors out there that are older than 386. Mostly they are new, and they all follow almost the same instruction. They are compatible with the 386 processor. Their instruction set is the 386 instruction set is supported by all these new processors, and that is the reason we are using 386.386 directive to tell the computer to use 32-bit instruction set or 32-bit architecture. Alternatively, what are the other options that you can use? You can use 486.486.586.6axis. Their privilege modes are like, if we use .486 or 586, for example, and then we have P. So 586P is a privilege mode. Similarly, for the 6 and 6, there's a privilege mode, and so on. However, .386 will be the most compatible instruction set with all the other. As I told you, that .386 or 386 instruction mode is the instruction set is the most compatible, means it is compatible with all the new architectures that we are using currently nowadays. Okay. Then the next directive that we use is called the model directive. We have used model, flat, std call. We have used in all the programs. What is the reason and what is the purpose of this model? Actually, this is the syntax, how we can use this model instruction. You can see here. So first we have to write .model, and then we have to write memory model, whatsoever the memory model option is. For example, here we are using flat. Then we have the language type or language and stack options. Language type and stack option. So this memory model is compulsory parameter. This memory model parameter, this one is compulsory. We have to define the memory model, what type of memory model we are using. Right now we are using flat memory model, even though our 32-bit architecture and our Windows, they are using the flat, means whole memory is considered as without segments and so on. So you can access any memory point or memory address directly. So this is the required parameter. It determines the size of the code and data pointers. Right now, if we use flat, then there's no limitation for the size. On the other hand, if we have, there are other options that we will discuss in the next slide. That if we use 16-bit architecture, then what will be the memory model option? What will be here, like small, tiny, and other options. The next language option is here. This is optional. If you want to use, it's okay. If you don't want to use, it's okay. But here we use std call. So this language type which we are using is the optional parameter that sets the calling and naming conventions for procedures and public symbols. Means how we call procedures, how we assign their names, and so on. So this is the calling procedure and the naming procedure for the naming convention or the way for the procedures and public symbols that we are using in our assembly language. This stack option is used when we use a stack segment or something, but in case of flat, we can use a stack segment. It is automatically assigned. However, this stack option is not used if memory model is flat. It's automatically being assigned, and a stack pointer is assigned automatically. There are other options like near stack and far stack. If we can use in 16-bit or other memory models, like here we are using flat, and there are other like tiny and small and so on. In that case, we can use near stack, like it groups. In case of, there are two options, near stack and far stack. In case of near stack, what will happen, data segment and stack segment, they will be, our stack is maintained inside the data segment. There will be no separate stack segment. In case if we use far stack option, then what will happen, data segment will be different and the stack segment will be different, and we have to define the stack segment limit, that what is the total number or what is the total limit for the stack segment and so on. So in case of near stack, they will be in the physical segment, same physical segment or physical area inside the memory, both data and the stack. These are the options. You can see here the parameters, like memory model, then language type, and then a stack option. In case of 32-bit, it's not used. We don't use a stack option at all. It's automatically assigned. And then we are using in 32-bit, we use only flat model. And language type, there are two, either C or std call. Either you can use both. You can use std call or you can use C. And stack option is not used in 32-bit values. If you want to use 16-bit architecture or 16-bit values or 16-bit options, then there are different options for memory model and language type and so on. What is the memory model for 16-bit values? So they support for the earlier 16-bit development, which we use for the 16-bit architecture and so on. So the other options are like for the 16-bit tiny, small, compact, medium, large, huge, and flat. Now if we use tiny, small, then the memory size which is assigned is varies, like 64K segment size and so on. So it will vary. If we use tiny, it will be small. Tiny and small, the size is very less. For the compact and medium size, for this code segment, all these segments is a bit larger. For the large and huge, the size is very much large. You can reference for this one the MSDN library online. You will get all these options. For the language type, for 16-bit earlier architectures, there is you can use C option, basic option, Fortran, Pascal. You can use syscall, you can use std call, and so on. So a standard call is the standard assembly call, which is being used for the naming conventions, how you can define name, for the procedures and their calling mechanisms. And for the 16-bit, you can use near stack and far stack. So in this case, when we use 16-bit values, definitely we will use all these segments, like stack segment, code segment, program or code segment, data segment, and extra segment. And in that case, you can use CS, code segment, along with some offset to access the. But right now, if you see in our previous lecture, we never use stack segment. We never use the data segment or some other segment like code segment along with the offset. We use only instruction pointer. We never use code CS register, CS plus the instruction point register. No, we directly use the instruction pointer and so on. So there's no need for the 32-bit values architectures. But for 16-bit, when you define either tiny or so any of the memory model, definitely it will divide whole memory into different segments, and memory is accessed through the segment registers plus offset that we discuss in our real and protected mode memory access. And you can see here the example. So we have model. So this is the directive, and flat is the model for the Windows programs which we use like 32-bit architecture. std call is the parameter passing method used by Windows functions, which means you need to push your parameters from left to right, from right to left. So when we push parameters, they are starting from the right. First option will be pushed first, and then so on. So this is the method when we push all these parameters in our functions or Windows function and so on. Here one thing you have to note, that the flat memory model uses 32-bit segments, and it must be preceded by 386-486 directive. Means before using the memory model flat, here you can see if we use flat, there should be 386 or 486 and so on. Why? What is the reason? Because 286 is a 16-bit architecture, and the previous architecture 8085, they are 8-bit architecture. 8085, before that one they are 8-bit and 4-bit architectures and so on. So you just be careful. If you want to use 16-bit, then definitely you can use other tiny or so on. But if you use .386 or .486, then be careful that before using flat you use .386 or .486. Otherwise you will get error in the program. Option cache map. So this option cache map, if we use none, it means the labels or all the variables or the procedure names and so on, they are case sensitive, which means that if we use hello, the word is hello, for example, for any variable and or procedure so on, and H is capital, and that is not similar to the word or the variable name hello whose H is small. So they are treated differently. So you just be careful. If we use option none, then it will be case sensitive. What is the reason to use this case sensitive? Because there's a very good programming habit. Most of the programming languages right now, like C or other programming like C++ and so on, they are case sensitive. So be careful. Or this is, you can call it, is a very good programming convention if we use our programming habit to use the case sensitive. Now there are some include files which we use. These include files are required when we are programming in the Windows environment or when we are programming Windows in assembly language. First one is the windows.include file. This windows.include file, it's always included. Why? Because it contains the declarations of the Windows 32 API, constants and definitions. When we program Windows, for example, inshallah, in the end, when we will discuss about the assembly language integration with the high level languages, how you can create windows, how you can create menus inside the windows, how you can create pop-up windows and so on, like the notification windows and so on. So when we will create, we will use this Windows include file. Even though we are not using Windows inside our programs, we are not creating Windows in our programs, but it's a good habit to include most of them in your program to avoid the errors and so on. And the kernel, we use kernel 32. It has different functions, like we use exit process, we use invoke, exit process, and comma 0 and so on, or maybe sometime we use null. When the name kernel is derived from the concept which is used in the operating systems. So this is the core of the operating system, which handles all the operations of the system. So everything, the operation system manages the whole system, memory, processor and so on, controls the input output systems and controls memory and so on. So if you want to perform interrupts, like we want to transfer control back to the operating system like Windows and so on, all these directives that we will use, we must include the 32-bit kernel 32 include file. For example, here we are using as exit process, means we are exiting from this assembly language program and transferring control to the Windows 32-bit operating system, or transferring control back to the kernel or the Windows operating system and so on. There are other two, like there are library files. For one are include files, other are library files, like kernel 32, masm32.lib, their extension is .lib, you can see here, and include have the .inc, and their directories are different. As you saw in previous example, our Microsoft assembler is installed at C, so its directory here actually it is on C. So we don't write C. This is the main directory, then 32 is a subdirectory, and the other directory where include files are is the include directory. Here we use MASM 32, 32 and so on, and the kernel 32.include files and so on. So these library files are libraries which we include in our program. They provide functions which are needed, function needed libraries in order to provide all these functions inside our assembly language. For example, we have function declarations, and the actual functions are defined inside the library files. Inshallah, we will create these library files. We will create our own functions. Then we will create their library files. So we don't need to write again and again all those functions. Once we have created those functions, and once we created those libraries, we can directly call or include that library, and those functions are the procedures which we define or which we discuss in our previous example. For example, I can give you one example. If we add two numbers or add the contents of an array, those examples which we discussed, we can create their functions or we can create their procedures. We can use those, we can save them inside the library files, and we don't need to define again and again all those functions or the procedures. What we do, we just call our own library file, use it inside our program or include inside our program, and then we can just use. There's no need to define again and again. So these are the library files which we are currently using. Next section of this lecture is about the input and output instructions. Now, in our previous examples or previous lectures, what we did, all those instructions that we discussed, they were only for the manipulation of the registers, jumps and so on, control, transfer, comparison. So everything which we saw, it was their output was inside the registers. Here we have EAX register, EBX register. So we only watch these registers, what is inside them, how operations are being performed. We never saw anything on the as an output like on the console. Console is the, I can write here. So there's console. Console is the DOS window or the command prompt window. So this window, if we want to see any output on this window, for example, if I want to print any message, if I want to print the value of register, if I want to get the input from the keyboard and so on, and assign it back to the any variable and so on. So we will use this IO instruction. So now we are going to provide interactivity to the inside our programs, so that programs can show us some output and receive input from the keyboard and so on. Right now we will just do very simple STD, the IO instructions. Then we will make them more complex, like to increase their functionality. Now here the first instruction which we are using is std in, to receive the input from the keyboard. Now what is inside? If you want to use std in, then definitely one thing, MASM 32 is required for this std in or out IO instructions. So these are the instructions which are part of this assembly language, MASM 32. Now from where I got all this information which is included inside the inside this slide, on this slide, is from the C drive, MASM 32 help file, and masmlib.chm, or this is a help file or compressed help file and so on. So you can get all help about all the directives, and instruction, or instruction, compare, jump and so on. Even though the memory models and so on, whatsoever we studied right now till now about the assembly language, you can go inside this help file or help directory inside the MASM 32, and there are different help files regarding different topics. For example, this is the about the libraries, how you can use these standard calls or console programming conversions and so on. If you want to have the directives like the instructions, AND instruction, OR instruction, there is a separate file, help file. If you need help to how to use help or how to use this assembly, it is also available inside this directory. So this is just like one tip. You can go there. You don't need to go anywhere else on internet. Sometimes if you don't have internet and you are programming alone and you need help, you can directly go inside this help directory and see these help files. Now first instruction that we are going to discuss right now is the stdin, and definitely this is called the standard input. So instruction, this standard input instruction will get the input from the standard input device. The standard input device that is available is the keyboard, definitely, and standard output device where our information will be forwarded is the definitely monitor. So we will use these two instructions, stdin and stdout, to receive input and send output to the input and output device. So for this instruction, you can see this is the structure, or you can see this is the syntax of this stdin. Actually it is a procedure. Stdin is a procedure which is defined in the libraries and include files. And here is the buffer. This is the LP size buffer, and is a double word, and then the length of the buffer. Now here there can be any variable which must occupy some area inside the memory. So whatsoever the input we will receive, it will be forwarded to that area inside the memory. For example, here we define like A, B, C, or A, B, C 100. A, B, C is the byte, for example, 100, duplicate, and nothing, for example. We do not assign any value. So what will happen, ABC will reserve some area inside the memory, and this reserved area can be used for any purpose and so on. So what will happen here, we will receive any input from the input keyboard or the standard input device, and then how long or how much input we can receive. So all this input, we will define length here. If you can see here, so buffer is a variable. This is the name of the variable. This name can be A, B, C, and so on. And this is the total size of this buffer, means how many bytes you can, or how many characters, or how many key presses, or whatsoever you can call. This is the total size of this buffer where it saves the input or the data we are receiving. So how we can use, there is one directive, it's called the invoke directive. The invoke directive is, we have seen the call directive or call instruction. This call instruction is used to call the function, but it doesn't automatically saves all those parameters inside the stack, but invoke automatically saves the parameter inside the stack and automatically pushes parameter inside the stack which are being used when we are calling this function. For example, there are some parameters like here the address, and then other parameters which we are using, they will automatically be pushed inside the buffer. So we use invoke to call this stdin procedure. Stdin or stdin procedure, here you can see we call this stdin procedure by using invoke, and so it receives text input from the console and places it into the buffer required as a parameter. Okay, so buffer is used as a parameter, but there is one parameter is called the address keyword. It will, or sometimes we use the offset. As we saw, there was an offset in directive or offset instruction. This offset option will give us the address of this variable, where the starting address inside the memory, the starting address inside the memory for this buffer variable. So it will give us, so here we are actually passing the starting address, and this one is the total size reserved inside the address. So when we receive input from the keyboard or somewhere, from input device, it must be directed towards this area. So here this function or this procedure will be terminated until you press the enter key. When you will press enter key, then this function will be terminated, or the function of this procedure will be terminated, and it will exit from this procedure. There are two parameters. One is the LP size of the buffer. So this is the input buffer for to receive text or anything from the console or from the input device, and length is the length of the buffer, or blen is the length of the buffer. As I told you, here this is the address and here is the size of the buffer or length of the buffer, that how many bytes it occupies. This procedure doesn't return any value. There is no value which is being returned by this this procedure. There can be procedures who return value, but right now this procedure doesn't return any value. Then the next instruction is for the output, that is called the std out. The same instruction, but here you can see whatsoever the buffer is where your text is stored, you can print that or send that text to the output device. Now one thing, our text is A, B, C and so on whatsoever. This is stored somewhere inside the memory, but here what we are doing, we will pass the address. For example, there is address message 1. Message 1 is the name of the buffer area or name of the string or whatsoever you can call it. So this message 1 is it starts from here, and there is a size, for example 100 bytes, 200 bytes, 300 bytes and so on whatsoever, 20 bytes, 30 bytes and so on. We define this message 1 inside our data portion, and we assign it some message, for example hello world or any message, what's your name, or what's the input, what's the output, enter your name and so on, any message you want to print in your assembly language. So we are actually passing this address of this message. So we are only passing the starting address. A starting address which is being identified or shown by the word or the name of this buffer, that is called the message 1, and we don't know the length of the exact this message 1. So what does it do? We define 0 at the end of this buffer or message area, whatsoever the message is, we use 0. So it is called the 0 terminated string. 0 terminated string. You will see the inside the example that this std out prints out or send the buffer area that is to be printed over the screen or on the screen or the standard output device. That text must be terminated by the 0. Here you can see, so std out will display a 0 terminated string at the current position in the console, whatsoever the current position is. Then the parameter is the text parameter or a 0 terminated string that we want to print. So there is no value that is being returned, so it will just receive the parameter and print out. There is no return value. Here is an example. Here you can see there are we have used two messages, message 1 and message 2. So these two messages, they will be used. And one thing you can note down here, here we are using data, and we can also use data and question mark. When this is the standard way, even though you can use this one here in this under this dot data directive, but if this is the standard way to define the undeclared or undefined registers. For example, here we do not define any value for this buffer, so it is as it is. So we do not define any value. We don't know what is the value, because we are just reserving this area, and we will receive value from the keyboard. So what we do, we will just define undeclared and data, and we use data and question mark, dot data and question mark. That was about this one. So here we define only two messages, two variables, message 1 and message 2. All these are the string. So string starts from here, the first character is T, the last character is space inside this parenthesis, and the next character and exactly the last character is the 0 here. Inside the parenthesis we have a space and then colon and name and so on whatsoever. But this string is terminated by the 0 value. This is part of this string. Here you can see TYPE 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. So the size of this string is 17 bytes actually. Is 17. It's not only 16 because space is here and 0 is part of this this message 1. Similarly, another variable has been defined. Its name is message2. Now first message or the first variable or first string is type your name. Second string is your name is something something whatsoever. There is nothing defined here. What is the purpose of this program? This program will receive, first it will print something, then it will receive information from the keyboard, and then it will display that information. So first it will receive, then it will display. Now first message is type your name. So what we will do here, we'll write invoke stdout and address of the message 1. When we write the address of the message 1, so it will print the message 1. When it will print the message 1, first it will do what will be the output of this program. We will traverse step by step. So we have a window. This is the console window or the command prompt window. So this command prompt window here, you will get the, first it will print this invoke stdout. So we are calling this stdout instruction address of this message 1. So it will start printing the message 1. What is inside here? It will say type your name and colon and some space. So the cursor will be here at this point. Cursor will be at this point. And then the next instruction is invoke stdin address and 100. This is the size of the buffer. So buffer is a variable. Buffer is a variable which occupies 100 spaces or 100 byte space. And what will it do? It will wait. This instruction will wait to receive information from the keyboard. So here if you will type anything, for example ABC or name whatsoever, these is a computer organization and so on, whenever you will press enter, this function will terminate its execution and program will come to the next instruction. Now you can see whatsoever you will type, it will be stored here inside the buffer area or inside this name buffer. You can give any name or assign any name for this area, but actually whatsoever you will type, it will be stored in that area which is reserved by the name buffer. Okay. Now if you invoke stdout and we are going to print out, definitely we are going to print out the message 2. Message 2 is your name is, for example, your name is, and then there is a space, and the next instruction is also again the printing. What we are going to print, whatsoever you typed through your keyboard, it will be printed here, or it will be displayed in the same manner. Whatsoever you typed here, it will be displayed in the same manner at this point. And then the next is also the stdin to receive input whatsoever. This is that if you are continuously running the program, there are other instructions which will replace this one, but here this stdin will wait until you type anything or you press enter key. So if you type anything here, this will receive input. Actually we use this one so that program just wait, doesn't exit when you press enter key and so on. So this will provide you some pause or some point where your program will wait for some text or any input. But as we know that stdin will terminate its execution only when we press enter. So when we will press enter, then the next instruction is to exit from this assembly program and transfer control main back to the main operating system. Now this is a program that is very simple program. Now during this program or inside this program, we did not consider any register at all. For example, whatsoever we receive from the keyboard, we want to transfer it into the register, or for example we are receiving in a text format. Sometimes we input numbers. hexadecimal numbers or decimal numbers, and we store them inside the variables. But if we want to use that value or number to perform some calculations, addition, subtraction, or other operations, then we have to take that value or take that ASCII number or ASCII values from that buffer, convert them into the actual number, because if we type 1 0 1 0 2 3, for example, this will be, if you type, this will be considered as a text. For example, here we are going to reserve this area which will hold this text, which is responsible to hold the text, means all these bytes whatsoever. Then what we have to do, we are typing a number actually, but actually it is being considered as a not as a number but as a text or a string. So we have to convert it 1 0 1 0 2 3 and so on into some decimal and assign, or some hexadecimal whatsoever, and assign it to the register so that we can perform some operations. So this is very simple program, just to receive input and display output. So now by using these instructions, and in future there are so many other instructions that we can use, like print instruction and so on. So we will use other instructions also. So this is the starting point. You can explore, there are so many other instructions that they are used as an input and output and so on. Even though we will do some Windows programming where you can show everything inside the window, for example pop-up windows and so on, error messages, when you receive error messages, then there's a window, and inside window there is some message that you have typed wrong, or you did something, or this is the error. So even though we can use those windows to program or to display some text or messages and so on. So this is very simple program, just output and input, simple. The next part, the third part of this lecture is about the jump instruction, but this is not the normal, this is not the unconditional jump, but here is a conditional jump. Now it will not jump to any label without testing anything, no. There are some tests based on some condition, either there are different conditions, either the values is or less than, either the carry flag is set, either the zero flag is set or unset and so on, either integer, unsigned integer is greater than, unsigned integer equal and so on, either the signed integer is greater than, equal, greater than, less than, not less than and so on. So there are different conditions. Based on those conditions, actually even though if we use signed or unsigned, for example, you saw in compare instruction, when we CMP instruction, we have used this compare instruction. It can perform comparison between two source and destinations, and it modifies the flags accordingly. Like zero flag, if we compare two values, unsigned values and so on, the zero flag will be set if they are equal, and if it is less than, means destination is less than that one or greater than that source and so on. So the sign flag or the carry flag and the zero flag, they will be different, they will be modified accordingly and so on. So a conditional jump instruction branches to a label when a specific register or flag conditions are met. A specific register or flag conditions are met. Now actually everything is done based on the flags. Even though if we use signed or unsigned comparison, or signed or unsigned conditions, signed or unsigned values, or register values or whatsoever, at the end what happens, the flags are changing. Flags, registers are either set or reset. So all these, whatsoever you will study in the based on the sign, based on unsigned, based on comparison, based on flags and so on, everything whatsoever we will study, actually at the backend side we are monitoring the flags, but here we categorize them. We are not concerned about the flags, so it is very difficult to monitor that what will be the flag. So we use sometimes unconditional, means the comparison instruction either is less than, one register contents of one register are less than the other register, one contents of one register is considered as an integer unsigned integer, either they are less than, greater than, and so on whatsoever. So the conditional jump, actually all the conditional jump instruction, they start with the word J. They start with the word, I will just select the color that should be red, so highlight. So it will always, all these instructions, they always start with the keyword or the word letter J. Just like there were loop instruction, they were also used to loop or to transfer control or flow control instruction. This is the conditional flow control instruction, and all these jump related instruction, they start with the character J, and there is condition also. For example, JB and JC, okay, jump when carry and jump when 0, jump equal, jump below. Below means destination is less than the source and so on. Jump below, jump equal, and there are some jump sign, jump 0, means these are for the carry flag based on the flag. These are some examples. We will see all the instructions in the next few slides. So if the carry flag is set, it will jump. If value is below than the next value, it will jump. If both the values are equal in the registers and so on, or maybe if we are comparing two registers by using compare instruction, if they are equal, then it will jump. Same, this here you can see jump 0 when we perform comparison between two registers, and if they are equal, what will happen? 0 flag will be set, or at the same time we can use the other instruction, is called the jump equal. Here jump when below means when the destination is less than the source, or at that time carry will be set. So if either use jump below or jump carry, both are same. So instead of using this jump carry, you can use jump below, jump equal, jump when sign flag is set, jump not equal, or jump not 0 if two values are not equal, or jump not 0, jump when ECX is equal to 0, when ECX registers contents are equal to 0, and so on. So these are some examples. Now we will analyze, or we will see all the possible combinations or all the possible jump or conditional jump instruction. And if you recall, unconditional jump is JMP. Unconditional jump instruction is JMP. In some other languages, unconditional jump is only shown for J only, not JMP, only with the letter J. Okay, now jump condition ranges, how far it can jump. As we already discussed, like in 286 or the previous modules, we use segments, and there's a limitation. You can use the offset inside the code segment or somewhere else whatsoever. So jump before 386, 286 and 16-bit and the 8-bit processors, architectures, what will happen? The jump must be in between -128 to +128 from the current location counter or current counter and so on. So you can jump inside the code segment like 127 in the positive direction, or below the program, which is continuous, or above the program, and so on. And this is the maximum counter you could use. But in case of Intel architecture, Intel's 32-bit architecture processors, or the processors who are 32, who are using the 32-bit architecture from the Intel, 32-bit offset permits, because we have the 32-bit size instructions, the address size. So 32-bit offset permits jump anywhere inside the memory, so you can jump anywhere inside the memory. Okay, this is one note. Now jumps based on the flag registers, jumps based on the flags. So the mnemonics, here you can see, first of all you will see here on all these next slides. So now we are going to consider all the possible cases of jump. Description, mnemonic, description, and flags. What is the condition, what is the status of the flag when this jump will be carried out, or this jump instruction will jump to the label. And one thing here, there should be label. I'm just going to write here. So here it should be a label here, some after this JZ. We will see examples also, but here I want to see, so there should be some label. So if this condition met, if condition is met, it will jump to this label. So JZ, jump if 0, means when 0 flag is set, when 0 flag is set, it will jump. Now if you are performing any operation and which you think that it will set or reset the 0 flag, so if you want to perform jump based on this condition, then you can use JZ. And maybe you saw that in our previous program we used jump and 0 when we use compare and other instructions, compare instruction especially. The other instruction is jump not 0, so you can see, you can extract the definition from here. Jump not 0, if the 0 flag is unset or is not set or low or 0, then this instruction will jump to the label. Then similarly for the jump carry and not carry, jump if carry or jump if not carry. So if carry flag is 0, then J and C will jump towards the label. Is JC will jump if the carry flag is 1. Overflow, jump if overflow, jump if not overflow. Sign and not signed. Jump if sign means if the sign flag is 1. Jump not sign means if the sign flag is 0. Similarly is JP and JNP. JP and JNP, parity flag. So jump if parity flag, whatsoever the operation you are performing. So for each operation, whatsoever the number of ones are there, if the number of ones in the result are even, then parity flag will be 1. Otherwise, if the number of ones are odd, then it will be, parity flag will be 0. So if you want to jump based on the parity flags or number of ones inside the result, then you can use JP or JNP. So JP will jump if the parity flag is high or the parity is even. JNP will go to forward or transfer control towards the label when the parity flag is 0. Other is jump instructions or conditional jump instruction based on equality. Now there are two values. For example, there are two values, and these two values are being compared. If the first, there's one operation 1 or operand 1 and operand 2, or one register another register, if we compare those two. For example, if we say this operator is less than this operator, or either they are equal and so on. So jump equal if both the left operand is equal to the right operand. We will see a few examples about the jump equal. And the opposite is jump not equal, if they are not equal. Jump CX is equal to 0. The 16-bit register, CX register is equal to 0. 32-bit registers, ECX register is 0. So there are, based on the equality, we are using these these 4 instructions. Then based on the unsigned comparison. Now flags, then we have comparison, and now we have unsigned comparison, and then there will be signed comparison. There is difference between signed and unsigned, so all these. So what we will see here, similarly you saw the difference when we compare, use the compare instruction for the signed and unsigned values and so on. So if we use jump A, means jump if above, means if the left operator is greater than the right operator. Okay, so I mean the destination is greater than the source and so on, if we use as a destination and source. Okay, J and BE, jump not below or equal. So JB is a jump below, J and B is the not below. Jump above and equal. So here jump above, jump below, so they are opposite here too. And here you can see we will not use operators here, these left and right operators. Here we will use only labels. Just keep in your mind that here we will use only label. So this operation has been performed before this jump instruction, immediately before this jump instruction. So here all are the labels. This is a label, this is a label, and this is a label, and so on. So here these instructions will jump based on this condition. So jump A, jump when above, jump not below or equal. If the left operator, mean they are not same, not below or equal. Okay, so it is similar to jump A or jump above. Not below or equal means same as jump A. Jump A or jump above or equal if the value is greater than or equal when we write. So these two have the almost same operation, jump above or jump not below or equal. There is jump above or equal, jump not below, jump not above or equal. So this one is equal to jump below. Not above or equal means the left operand is less than the right operand, and so on. Jump below or equal and jump not above. Jump above, not above is equal to jump below or equal. Now can you imagine one thing here, that there are multiple instructions. They have almost similar operation, but the opcodes, the number of opcodes are very large. There are 2, 4, 6, and 8 for this unsigned comparison, and almost 3 instructions or 4 instructions are same, or the instruction who perform the same operation. Almost these 8 instructions 4 perform the same operation, almost. Like here you can see jump above and these jump not below or equal, they have same, and jump above and equal, and these two are jump not below, they are same. These two are same, jump below, not above or equal, and this one. They are similar. Why they have multiple instructions who have the same operation? CISC, complex instruction set computing. So instruction set has a very large number of instructions. You can visualize here from this slide, there are multiple instructions who perform almost similar operation, so there are multiple. The number inside the instruction set is very large. Definitely this instruction mnemonic has different bit pattern, J and BE, which is equivalent to jump above. It has different bit string. So that is the reason we call it CISC. We don't call it RISC. RISC is the reduced instruction set computing, and so on. We will compare these two. What is CISC and RISC. So in the complex instruction set computing, the number of instructions inside the whole instruction set is very large compared to the RISC. Now we will see the other comparison, the other jump instructions. Inside this slide you can see jumps based on the signed comparisons. Now we assume that all these operands which are being used for comparison, they are signed operands, means we are considering them as a signed numbers, or the values inside them are signed. I mean the leftmost or the most significant bit shows the sign. So here you can see JG, jump if greater, just jump, and JA, jump above, or JG, jump if greater. It's almost similar for the JA, but JA was for the unsigned, this one is for the signed. Jump not less than or equal, or it is similar to this one. They both are same. Similarly these two are same. We will see. And these two. But you can use all these instructions in your programs. For the conditional transfer, we will see how we can use conditional transfer when we'll do their programs in assembly language. So here is a label, and all these are the labels. here at this place after this one. Okay, so jump greater, jump not less than or equal. Not less than or equal means if the operand is not less than or equal to the another operand. Then the next one is jump greater than or equal to if left operand is greater than or equal to the right operand, and so on. Jump less than means if the signed value inside the operand, left operand, is less than the signed value inside the right operand, and so on. Jump not greater than equal is same as the jump less than. Jump less than or equal, jump not greater than, and so on. So these are the jump instructions that are based on the sign comparisons. Here you can see the examples right now. Now, for example, the task is we want to jump to a label if unsigned EAX register is greater than EBX. So both the values are, both these register are considered to have unsigned value. Their values are unsigned. What is the solution? We use compare followed by the jump A. So the label, we will jump to a label if EAX is greater than EBX. So jump above, we know that this one is for unsigned, is for the unsigned, and so on. Compare for the unsigned. For example, here you can see first instruction is the compare instruction, and this compare instruction, there are two, so destination and source. So if EAX is greater than EBX, EAX is greater than EBX, so jump will be performed. This larger or larger, whatsoever this keyword is written here or label is written here, it is the label, shows the address inside the program, so it will transfer control to this label. So we use compare instruction. It must be followed by the jump. So because there may be other, if you use other instruction, just keep in your mind, if you use other instruction here, for example addition or other instruction whatsoever, even though std out or std in, if you use those instruction, what will happen, they will modify the flag registers. So just be careful. The compare instruction must be, if you want to use jump or conditional jump instructions, if you want to use conditional jump or conditional flow control instructions, then the test instruction or comparison instruction or test instruction, whatsoever the instruction you are using, it must precede immediately. It must be immediately the previous instruction. So first instruction, for example, with this one, then the immediate instruction should be the conditional flow control instruction. Second task is, if we want to jump to a label, if signed EAX is greater than signed EBX. If these two values are if these two registers contain the sign, then definitely we will use JG. As we discussed, jump A and JG, these are two similar instructions. They perform when left operand is greater than the right operand. So this is the left operand, here you can see, and this is the right operand. So if the left operand is greater than the right operand, what will happen in case of signed one, we use JG. So JG instruction, this will jump to this label or this address. So at this label it will jump if the value of signed value of EAX is greater than the signed value of EBX, and so on. So next application is, the task is jump to label L1. For example, there's L1 is the label name. Here you can see we want to jump anywhere at this label. If unsigned EAX is less than or equal to val1. So if unsigned EAX, so jump when below or equal, or its signed one will be different one, you will see here. So we will compare EAX with variable. The label variable name is val1. So if val EAX is less than or equal, then it will perform jump to the L1. Just see here, for the signed version, we will jump less than or equal, jump less than or equal, JLE instruction. Third application you can see, if the task is compare unsigned AX and BX and copy larger of the two into a variable named large. For example, if we can say if in C, if for example AX is greater than BX, for example, then what we will call, we can say that larger is equal to AX, otherwise or else we say large is equal to BX and so on. So this is actually the logic. So this is AND if, for example. So if AX is greater than BX, then large or greater than or equal to, for example, BX, so large is equal to AX, else large is equal to BX. So value, which we will compare two registers or two values, and whatsoever has the larger value, it will be moved towards the. So if you want to use is equal to or not, if you want to have the equality check, either they are equal or not, either the larger one is, which one is the larger. So here we will not compare either the equal or not whatsoever, but we compare which one is the larger one. We assume that they are not equal, one is larger than the other one. So first of all, BX, for example, so we have two registers, AX and BX. So first what we'll do, we will move this BX inside the variable large. So now BX is inside the large. Now what we will do, we will compare AX and BX. If AX is not above or AX is less than, not above the BX, then what will happen, we will jump here. We will do something else, because we have already assigned BX inside the large. So if AX is not above or not greater than BX, then we don't need to change the value of this variable large. Otherwise, if this condition is means if this comparison gives us the different value, for example, if AX is less than, AX is greater than, for example, BX, then what will happen, this jump will not be performed and value of AX will be transferred to the variable large. The next comparison is, for example, next test is, or next task is, application is, compare signed AX and BX and copy the smaller of the two into a variable named, this is the name of the variable, small. So this is almost similar, and so we are now using the signed one, and definitely for signed one we will use less than, greater than, not less than equal, greater than equal, and so on. So here the logic is, there are two values, so I don't want to write here, I can just discuss here. So if AX is greater than, less than BX, then small will have the value of AX, otherwise small will have the value of BX. So first of all, we will transfer the value of AX into small, then we compare BX with AX. For example, what we are going to say, if we compare, if BX is not less than means either equal or greater than with the compared to the AX, then we will jump here to the next this label. Otherwise, small, if a BX is smaller than AX, then previous value of small will be replaced with the new the value of BX, because BX is smaller than the AX, and so on. You can use the greater than JG also. If jump greater than means if you want to transfer somewhere else and so on, where the value of small will be changed or so on. So similarly, you can use any other jump not less than. So if you use jump greater than or equal, so you can use the same one, greater than or equal, and so on. So there are these instructions, there is a huge list of instructions. Now logic depends on you, how you want to use those instructions. how you can use those instructions. Definitely you can use compare instruction. We know the compare instruction. Now logic depends on you, how you are using. For example, if we want to use a loop, or if we want to without using loop instruction, if we want to use create our own loop, what we will do, we will assign one register one value of 10, then we will decrement, then we'll compare with value, either this value is less than or greater than, for example, the value of register is greater than 0 or less than 0 whatsoever. So we compare, and then we jump based on this one, then we decrement until they become equal, and so on. So you can create any type of loop, any type of logic by using all these instructions. This is the fourth application. You can see jump to the label L1 if memory word pointed by the ESI. So we are using the memory word or the memory items or memory elements here. So ESI points somewhere, so we using compare word pointer. If it is equal to 0, so if the value which is pointed by the ESI, the address inside the ESI, inside the memory, if it is equal to 0, then we jump equal. If jump equal, equal means if this value is equal to 0, so it will jump to the label 1. Another jump is it will jump to label 2 if the double word inside the memory is pointed by EDI is even. So we will use the test instruction whatsoever the address or area inside the memory is. If it is being pointed by the EDI, if it is equal to 1 or something, so it will jump to the jump when 0. So we are testing here, we are using the test instruction. We already saw the test instruction which perform the AND operation, how AND operation will be performed. Whatsoever the value is, we have to compare the rightmost bit. For one rightmost bit, this one is 1, other are 0, and so on, whatsoever 32 bits. If we want to compare, here you can see whatsoever the bit pattern is, we have to compare only this bit. So if we perform AND operation between 1 and the memory address, whatsoever the value is stored, then if the result is 0, it means it is even. If the result is 0, it means it is even. If result is not 0, then it means the value was odd, because odd value must have 1 here. So if we perform AND operation between these two, 1 and 1, result will be 1 and rest will be 0, and so on. So it will not be equal to 0. So jump 0 if the value is even. Jump 0 will be the result when this one should be 0, the rightmost bit or the least significant bit should be 0, then result will be 0. In that case, we will jump to L2. So jump when they are even. The last application is jump to a label L2. This is the task. Jump to label L1 if bit 0, 1 and 3 in AL register are set. So we have to test whatsoever their bit pattern is, we don't care, but we want to test either these bits are set or reset. Okay, here you can see first we clear all the other bits, except bit number 0, 1 and 3. So bit number 0, 1 and 3, 0, 1, 2, 3. So 0, 1, 0, 1 and 3. This is 2, this is the 1, I'm just 0, 1 and 3. So 2 number bit we are not concerned. So first we want to clear them. How we can clear them? We perform AND operation. 1, 1, 0, 1, and all these zeros, if they are already 0, they will become, or if they are 1, then all of them they will become 0. So bit number 2, bit number 4, 5, 6 and 7 whatsoever, they will become 0 automatically. If they are already 0, they will become 0. If they are 1, they will be 0. So whatsoever the value of this bit is inside AL, previous value, it will remain as it is. If it was 0, it will be 0. If it was 1, after performing this operation, it will become 1. So these 3 bits are unchanged. Otherwise, all the bits have been changed. Now what we are going to do here, we are comparing. AL comma 0 0 0 1 0 1 1. Now check the remaining bits. These are the bits which we are going to check. Jump and equal. Jump and equal. It will jump when they are equal, means equal will happen, or they will be equal in a sense when the value of AL should be 0 0 0 0 1 0 1 1. This is the case when they will be equal. Otherwise they will not be equal. If this one is 0, for example, this third bit is 0, 0 bit is 0, or 1 bit is, any bit is 0, it will be less than the this operand. So what will happen, we want to see either these bits are set. So why we need all these operations, like previously you saw AND instruction, or instruction exclusive, or now you can use all those instructions. Sometimes we want to see this, analyze specific bits, because those bits are used in, for example, error corrections, or input output flag, setting the input output pins, and so on whatsoever. If we want to set a specific pin, a specific instruction, so we use these bits. We want to set them or reset them, these specific bits. And even though we want to analyze those bits, then this is the logic where you can use them. For example, if I want to set the specific pins where the monitor the output of specific pins and so on, or the interrupts, whatsoever you can call them, so we can use these type of instructions. Now in the end, I will summarize what we discussed during this whole lecture. We discussed about the program components, like the processor directives and so on, like 386, 486, 586, 6 and 6 and so on. And we also discussed about the model, like the flat model and the naming convention for C and the STD call and so on. So there was flat, tiny, small and so on. Then we discussed about the input output instructions, like for example STD in, to print the buffer, to receive the input from the keyboard or standard input device is stored inside the buffer area. Buffer area address, starting address is defined here as a first parameter. Next parameter is the size of this buffer area. Next instruction was STD out. This instruction sends the output or the buffer area inside the memory towards the monitor, where this screen, on the screen where it will be displayed and so on. Then we discuss about the conditional jump instructions. So conditional jump instruction based on the flags, based on equality, based on unsigned and signed comparison. So this is end of the lecture number 18, and inshallah in the next lecture we will analyze all those instructions inside the assembly language, and we will see the behavior of those instructions. We will create some programming logics and so on. So this is end of this lecture. Till lecture number 19. Allah Hafiz.